Hello everyone. In this first video about reinforcement learning, I'm going to talk about terminologies that are needed in order to understand reinforcement learning. And in my future videos, I'll talk more about the equations like Bellman equation, solutions of that, Q-learning, and other things. And hopefully in the last one, we'll talk about the neural network solution or deep reinforcement learning. So first, let's look into terminologies, the terms that you need to know before we can even look into solutions. What is reinforcement learning? First of all, reinforcement learning is one of the three major paradigms in machine learning. If you watch my video on machine learning, Introduction to Machine Learning Terminologies, I have two videos of that under this playlist, Machine Learning. You know that there is supervised learning, there is unsupervised learning, and there is reinforcement learning. Now, some people add a fourth category of semi-supervised learning or something, but I would say that's basically a product of supervised and unsupervised. So I personally do not like to call it a fourth paradigm. So we talked about basically supervised and unsupervised methods in machine learning. It's time to talk about reinforcement. Now, reinforcement, one of the interesting thing about it is bio-inspired. Why? Because here you send an agent to an environment and it interacts with the environment, and then based on each transaction it does with the environment, we call it an action, it either receives a reward or a punishment. And the goal of it is to learn the behaviors that will give him the maximum rewards and the minimum punishment, okay? And this is how we all learn in real life as a kid, if you look at animals and so on. So you see that when a kid does something and the parents, yell at that kid or frown at him or anything like that, right? Or give him a consequence, he would learn, well, that was not a good idea to do that. I'm not going to do it again. But if that kid does something great, he or she will learn that, well, that was really good. My parents basically gave me lots of compliments. They bought me something. They gave me a cookie, right? They praised me in front of my relatives, stuff like that, friends. That is a good one. That is a good reward. I need to do more of that. So that is how in reinforcement learning you learn the best behaviors, which here we call policies. Okay? So let's look at some of these terminologies here. Before I start, some of the pictures and material are taken from these websites. The two of the pictures are taken from these, and some of the text is taken from Wikipedia. So let's get to it. The first thing is the agent. Agent is what or who is interacting with the environment to learn, okay? That is the learner, that is the decision maker. Like for instance, if you look at the Mario game, right, Super Mario, it's that Super Mario, but really it's you, it's not the Super Mario. Super Mario on behalf of you will go into that environment and kind of jumps on those what you might call a mushroom, right? Or gets hurt or something, right? It's the mushroom gets bigger and all sorts of things. So you learn what kind of thing to do and what not to do. That is your agent. Environment is, of course, anything that your agent interact with. In this case, the Mario world, right? All of those uh, animals and the piranha plants and all of those, the gold coins, all of those things are basically what it is interacting with. The fire, the lava, all of those. What about the state? State is a representation of your current situation in the environment. So both the agent and the environment, if you want to represent them, how is the state representing them? For instance, if you look at the chess game, you know that in chess game you have these 64 cells, correct? And then basically based on those 32 pieces that you have, which one of them are present, which one of them are taken, and so on and so forth, correct? Then each combination of all of the black and white pieces and where they are in the chess set, that is one single state. So you see, states in games could be extremely complicated. And you might say, how many states could a game or a situation or a real life problem or anything have? Well, it depends. If the game is, or the situation in real life is discrete, so you only have a finite number of positions to move to, then maybe your state is also finite, but it could be very large. For instance, in chess, you might say how many different possible combination of different parts in different cells you can have in a state. And they say that in chess, it's typically something like 10 to the 43 possible combinations of different parts in different cells. Okay, yeah, that's finite, but that's very, very large. And exploring all of that is almost impossible. Okay, but if a robot is moving in an environment, and in that environment, it can be in any position and any orientation or with any velocity, right? Because the environment is continuous. Guess what? Now your state could be infinite. Okay, your state could be infinite because you can take on infinitely many values. So that is one of the biggest challenge, is when the states are very, very large or infinite. Again, exploring the environment is very hard. What is action? By the way, each state or action, as we'll see, they are defined for a specific time. So at time t, we say S sub t. Okay, that means state of the system at time t. The same thing for action. Action at time t. What is action? Is whatever your agent does in a specific state, whatever transaction it does, whatever interaction it does with the environment, right? So in a chess, any move that you make with any of your 16 pieces, you and your opponent, that is basically an action, right? Moving a bishop, moving a knight, anything like that, correct? In, for instance, Mario, all of these moves, left, right, up, and down, correct? Maybe throwing one of those, I don't know what they were, like a hot lava, or I don't know, something that it throw at those objects. All of those are basically actions. What about policy? What is policy? Policy is basically a strategy for how to take the actions, how to behave. That's the behavior, okay? How you should behave and how you should interact with the environment, what actions to take. And typically it is a function of state based on where you are in the game or in real life. You will take an action, correct? In chess, if, for instance, in the next move your opponent is going to take over your queen, your probably option is to move the queen, right? That's one of the options, right? A robot, if the state for it is very close to a wall, probably the action is to divert, right? Turn around or slow down or anything like that. So typically it's a function that in reinforcement literature typically shown by letter pi. So it could be f, but here typically they show pi of a given s. That's that upward vertical line means given, right? That's a conditional probability. So a given s. So if you know s, what kind of function would you choose to take actions? Now, to take an action, there are two ways to do it. Either you do a deterministic policy, so pi of s is equal to a. So if I give you s, you give me an a, right? Okay. Most of the time, it's not exactly like that, and you don't have these deterministic policies. Sometimes you do. Okay, for instance, if it's a robot going through a path planning, maybe it is a function of that, but typically, depending on the state, you might have several answers for A, not a single one. So this function could be a multi-criteria function, checking, right? Depending on the S, it picks some A, okay? So it's not typically a simple function like, I don't know, A equals sine of S, or a polynomial or anything. Most of the time, these are a multi-criteria function. Now, sometimes it's not perfectly deterministic. It's a little bit stochastic. What is that? So here, your policy is a probability of taking action A given that the state is S. Okay, so although you might have some average of this probability, some expected value, correct, of the probability, but still there is some variance, or in multidimensional, a covariance matrix around it. So you might take the expected value action, but you might take something a little bit off depending on how this probability function is defined. Okay, would you pick a Gaussian function? Would you pick any other function? So depending on that, you might take different actions. Okay, what about the reward? Reward is the essence for training. Of course, if you don't have a reward, and you might say, what about punishment? How would you reinforce punishment? Because you cannot just always give reward. If you do something wrong, you should get a punishment. So what would you do for punishment? In punishment, the reward still going to be there, but this reward is going to be negative. If this reward is a positive, for instance, which accumulates over time and gets bigger and bigger, that could be a reward, actual reward, and a negative could be a punishment, okay? So typically it's a scalar feedback signal that you receive when you take action A in state S, okay? So for instance, if in this Mario game, when that piranha plant is coming out of those pipes, correct? You see that piranha plant is coming out. If you jump right on it, okay, and you shrink down to the smaller version of Mario, guess what? You get a negative reward. You learn that you shouldn't have done that. But if there was this gold coin here, correct? If there was this gold coin, and you jumped on the gold coin and you see that you got one extra life, or your gold coins increased, that is a positive reward, okay? So you can define that, and this is really the art of the reinforcement learning designer, to define proper rewards and punishments, okay? That will affect your policy selection big time. Now, for at each time point when you take an action, you will get an immediate reward. But it's not just that. The thing is, in life, when we take an action, not only that action will have repercussions or feedback at that moment, it also will cause some feedback or repercussions in the future, right? For instance, if you invest in stocks that is going down, yes, today you might say, well, guess what? Today I was investing in some kind of stock of company that was going down. Well, it doesn't look like a good idea, because it seems like you're investing on something that is losing its value. So in the short term, it looks like, yeah, that was a bad decision. You're betting the dead horse, they might call it, right? But guess what? The stock market is not always going to go down. After sometimes it is going to keep going up. And the thing that you bought here when it was cheap, and you bought a lot of it, now when it starts going up, if it does, guess what? You bought it in the cheap position, and now it is going to go up and get bigger and bigger. And that's what most of these rich people do. They buy the stock when it's very cheap. Okay, and they keep it until it's very, very large. They made lots of profit, then they might sell it or might not, depending on the situation. So the effect of an action in future should also be counted for when you are picking a good policy or a bad policy. When you're deciding, you want to look at the total accumulated reward from this time t onward all the way to, let's say, for infinity, or whatever time that is the final time of the problem or simulation or whatever it is. So what would you do? The r of t plus 1 is added to r of t plus 2 to r of t plus 3 all the way to infinity. But what you do is the one that you get right away after taking an action is not going to be counted the same as the one that you take in 2 time steps from now, as the one that is taken in 3 time steps, as the one that is taken in 10 time steps. In other words, the one that are closer to you in time are rewarded bigger compared to the ones that are in the future. This parameter gamma that is going up in power as you move on in the future, this is called a discount factor. And it weights the rewards because this parameter is less than 1. The first one has a weight of 1, let's say gamma is 0.9. The second one has weight of 0.9. The third one has weight of 0.81, and so on and so forth, right? 0.72 something, and so on. So you see that the weights of the future benefits is not as much as the ones that are immediate. Because most of the time that's the case. They say a bird in hand worth basically 2 that are free, right? So you want most of us want to take immediate rewards, and that is another one of big hyperparameters in reinforcement learning. What to pick for this gamma? Because if we pick very small gamma like 0, literally means, hey, forget about the future. Only look at your current reward. Forget about the future. Only look at immediate reward. So that is really short time view. You might call it a myopic. But if you make gamma to go close to 1, means, hey, don't look right now. Look also in the future. So you're doing a long-term planning. And that's what I said. For instance, these people who buy the stocks when they are cheap, in terms of that, they are doing a bad thing. Why? Because if you look at them, let me show you in this formula. If you look, if this is time t, and let's say this is t plus 1, and then t plus 2, and t plus 3, and so on and so forth, at time t plus 1, you're losing your value of your investment. So this guy is going to be negative. The next one, you start to going up a little bit bigger than 0. The next one even bigger, the next one even bigger, and those bigger long-term benefits will easily outweigh this short-term loss. So at the end of the day, your total return is going to be very big. Okay, that's the same thing, for instance, when you do a chess. If in chess, you see when people use Gambit, right, and they sacrifice one of their parts for a bigger goal, that's the same thing. When you are giving away your queen, and the person says, oh, queen, guess what? I got some huge big weight. I got some huge gain. I got the person's queen. He didn't pay attention. He gave me his queen. I'm the winner. But then you see in a couple of moves, guess what? You are checkmated. Okay, so in that long run, you lost a lot more than you won. So totally you lost. Okay, so we have to always allow for some long-term planning if we want to get good policies, because the ultimate end or goal in reinforcement learning is this guy. The ultimate goal of reinforcement learning is to find the good policy, the good behavior. That's the ultimate goal of reinforcement learning. And if you don't allow long-term planning and use a very small gamma, you most probably have not learned the game very well. Like when you look at the grandmaster in chess, they look at several moves ahead of time. They read 5, 10, 20 moves ahead. But if you are very rookie in chess, you probably only look at 1 or 2 moves ahead. That is the difference between you and a grandmaster. Okay? So this count factor is a very important hyperparameter. Okay, now we said that policy is the ultimate goal, right? The question is, how would you come up with formulating this problem? How would you decide one policy is better than another one? So here you have to have a cost function. because ultimately reinforcement learning is an optimization problem. Okay, at the end of the day, it is an optimization problem. Find the policy that gives me the maximum return. Okay, something like that. So you have to define a proper cost function so that minimizing or maximizing that means finding the best policy. What kind of cost function would you define? One that is the most common and you see a lot is called the value function. Value function is typically the one that measures the goodness of being in a state or picking a pair of state and action. So if you were in state S and you pick action A, was that a good idea based on that policy pi? Was it a good idea or was it not a good idea? How would you measure the goodness of that? Value function is the answer. Now, how would you define this? If you only care about the state, then you can define state value function V of pi given S. So clearly this function is a function of state that you picked, but under policy pi. So you want to know what is the expected return, okay, following policy pi if you started from state S. So expected value of, look, the expected value of what? This important thing, the return, where the gamma is important. The expected value of the return, given that you start from position S, okay, under policy P. So initially you are in state S, and then you pick some policy P. It takes you from S1 to S2 to S3 and so on and so forth, okay? And each one of them comes with a reward, correct? So here you get RT plus 1. Here you get RT plus 2, RT plus 3. Then you weight them with some gamma, power of gamma, and so on. And you call it G. And then the expected value of this G, starting from this initial state and following pi, is your cost function. Okay, and the goal is to maximize this. What is the unknown? The unknown is the pi. What pi do I pick so I can maximize this V function? Okay, this is called state value function. Now, a similar thing can be defined for action value function. Okay, so this is when you want to look at the expected value of the return, given that initially you were in state S, you picked action A and you are following pi, then you call it Q pi of S and A. And again, you can basically maximize this one. Now you might say, what is the expected value here? What is the expected value doing? Remember, I said that most of the time your pi function, right, is not a deterministic function, it's a stochastic function. In that case, as I said, in order to look at the average value, you look at expected value, and that is exactly what we are doing here. So when your decisions are not 100% deterministic, but a little bit variability in them, then you have to use expected value. Okay, and again, the goal is to maximize this. How would you do that? We'll see in the next video. We'll talk about Bellman equation and the solutions to that. But here we just need to look at different terminologies. Another terminology that is very important is exploration versus exploitation. What is this? Exploration means, hey, try to look into actions that are new, so hopefully you can get better rewards. Exploitation means take the actions that you already know they are good and they yield the high rewards. Okay, so this picture that I took from one of those websites, this is interesting, right? So hey, I want to go out for eating. Do I go to the usual place or Do I go to this new place that just opened? They had the grand opening. Well, that's a gamble. That's a risk that you're taking. You know that usual place is the one that you like, and it always had good food. But if you want to go there all the time and exploit in it, you lose the chance of trying on the new things, right? And you might get disappointed. You go to this place, oh gosh, look, I spent a lot of money and the food was literally junk. Okay, that was a gamble. Or guess what? You go there, oh gosh, I thought this place is good. This is even better. I want to come to this. So it's a risk that you are taking. Exploration is all about the risk, because there might be some rewards that you don't know and you want to discover. Exploitation is to play it safe, to play it conservative, basically. So, and in reinforcement learning, you have to have a good trade-off between these two. Because if you always exploit, you might not achieve the optimum function, right? It's like the optimization problem. So let's say your V function that you want to minimize or maximize, it is something like this, for instance. So if you say, well, I'm starting here, I go there and I reach that top, the crest point, and guess what? I'm at my local maximum. I'm good. I say I converge. That's the best behavior is right here. That pi is my best behavior, my best policy. I stay here. But if you look down, a little bit down in the road, you say, well, look, that's flat and that's below where I am. I should not even explore either direction. But guess what? If you continue going along the way, you might be disappointed a little bit, but guess what? You're missing this big crest here, this big maximum. That is your actual pi star. That is your actual global maximum instead of this local one. So, but the problem is, if you always want to do that, first of all, it takes forever to converge if you want to look into all this space of policies. Because as I said, the number of states and the number of actions in many real world scenarios or even games is crazy, crazy large, and there is no way that you can explore all of it. So you have to only rely onto some samples, okay? And most of the time you cannot solve them deterministically. So you have to basically rely on simulations, Monte Carlo or anything like that. And you might never actually find the perfect global maximum. And you have to, at some point, stop and say, hey, I searched all of this region. And in this region, this is the best point. I'm going to stop. Because that one was really an isolated point nobody ever thought of. Okay? So you have to have a balance so your algorithm converges to something. It might or might not be really an optimum solution, but if you want to explore forever, you will never converge. If you want to exploit, always then you lose the big rewards, okay? Potential big rewards. So you have to have a trade-off. Okay, the last few things that we want to talk about is about the Markov property. The Markov property is something very important that is an assumption that is used a lot in reinforcement learning. What is Markov property? It says that, if you want to say it in plain English, it says that the future, whether it's a state or reward, only depends on the current state and action. It does not depend on the past, the sequence that you took in the past. So it says, if I know where I am right now, I should be able to predict my future. Whatever made me come to this point is not relevant. Okay, that is called the Markov assumption. In other words, if in terms of mathematics, it says that probability of ending in state t plus 1 given all of the previous states and actions from time 0 to time t is only the same as just looking at time t and forgetting about all previous ones. The same for rewards. The expected value of rewards at the next time point given all of the previous history, is the same as just the current point. The previous ones do not matter. Okay, so that is called the Markov property. In a pictorial format, if I'm in state st minus 1 and I take action at minus 1, I will end up at st. If at st I take action at, I end up in st plus 1. These previous ones, so if this one was s of t minus 2 and this guy was a of t minus 2, these guys will have no effect on this current thing. This one and this one, they are not connected. Okay, I don't have these. I only have basically these two. These are the only things that matter. Because the effect of these previous ones, is hidden inside this guy. This s of t minus 1 has the effect of at minus 1 and st minus 1 to it. So it's an implicit, basically, effect or contribution. It's not really an extra explicit one. So that is called the Markov property, which is used a lot to formulate reinforcement learning problems and solve it. And of course, the Markov decision process, or MDP, is basically something related to Markov property, which is defined by a tuple of 4 elements. S, A, the transition probability, and the reward. What are these? So the transition probability of going from state S to state S prime, or ST to ST plus 1, is the probability of ST plus 1 being S prime, given that ST is S and AT is A. Okay, this probability function, we call it the transition from one state to another one. This is called the transition probability. And similarly, the reward of going from S to S prime under action A and getting the reward is exactly a similar thing here. You see, S started at S, ST started at S, AT that you took is A, you ended up at S prime, and because of this transition, you ended up with reward RT plus 1, okay? So any process that you can define by these parameters is called a Markov decision process, and the important thing about it is they follow this Markov property, okay? Because you see here that basically the only thing that matters for time t plus 1 and the state for that is only time t, nothing beforehand. The same for the reward. All that matters for reward is the previous time point and whatever you ended up as a result of this. Okay, only the current time or the previous time matters for the current time, or current time matters for the next time. That's it. That's called the Markov decision process. Now, Markov processes could be, decision processes could be fully observable or partially observable. What is that? Fully observable Markov decision process, or FOMDP, is where that when your agent interacts with the environment, one of the important things that we have not discussed so far is this S. S means the state that you are in. Okay, the state of the agent and the environment. Do you always know that state very well, perfectly? Well, in many times the answer is no. Sometimes, well, it's just a game or something, yes. Maybe because you are simulating it, you have everything, but many times the environment is not easily known perfectly, or the sensors or the measurement devices that you have, the observation devices you have to measure the environment, they are not perfect. They have noise in them. They have uncertainty in them, okay? As I said, if you are in a chess game, guess what? At any point you exactly know the state of the system because you can see all of the chessboard and all of the chess pieces. So, of course, it's fully observable. But if a robot is going around in an environment doing SLAM or mapping or anything like that, correct? And maybe interacting with the environment, doing something, maybe collecting samples, let's say it's a Mars rover or something. Not always this robot knows everything. Like what? For instance, does the robot know exactly where it is? Or it knows exactly what is the velocity of it? Well, not always. Why? Because it has to do localization, and localization has errors. Okay? Because it relies on, let's say, odometry, which has drift. It can rely on some kind of sensors, could be a laser or a vision or something. They have noise and error in them. Sometimes it does not have GPS. Even GPS has error in it. So in those cases, the state that you think you are in is just an estimate, and it's what we call a belief state. This is an approximation of the actual one. So instead of having S, in this case, you have S hat. You have an approximation of the reality. You don't have the actual one. You have a belief state. Okay? And so in this case, you have basically an observation function, which is observing the observation O, given that you are in state S prime and A, or in S hat and taking action A. Okay? So you only take an observation, and the observation will lead to a belief state, okay? Not the actual state. And your policy that you pick will map your belief state to the actions, right? So it is pi of what? A given S hat, not S, because you don't have S. Okay? That is very important. Okay, so these are the 15 important initial terminologies that I wanted to tell you about the reinforcement learning. Now, 2 extra things that we need to talk about before we finish this video. 1, why is reinforcement learning so great and powerful? Because if you look all over the place, you see it. In anywhere you see who works in machine learning, in games, in interaction with environments, they are even training robots to learn how to, for instance, like a humanoid robot to design its gait and to move. They can use reinforcement learning instead of complicated mathematics equations and controls. They use reinforcement learning, so it learns how to take steps on the flat ground or going up and down the stairs or something. So it's all over the place now, and it's very, very useful. Why is it that this is so powerful? 1 is, as I said, in order to perform the optimization task, it uses samples. As I said many times, the space that you have formed by the states and actions, okay, S and A, is so large, like chess or any other even simple games, that there is no way you can explore the whole thing. So you only can approximate these transition functions, the reward functions, or anything like that by just samples. That's where you use, for instance, Monte Carlo simulations or anything to approximate these functions, okay? And to approximate the functions, that is the second thing, they use function approximation to deal with large environments, okay? So they use samples because many times you don't have an analytic function, and they try to approximate. So reinforcement learning in large environments can be used in these following situations. 1, where you know a model of the environment, but you cannot analytically solve it. Like if you have a robot and the equations of motion are highly nonlinear with friction, contact dynamics, and there is no way that you can exactly solve it. So you exactly don't know if you are taking, for instance, so much torque on each motor, what is going to be the angle of each joint at the next time point analytically. Yes, you can numerically solve that, but not analytically. because those second order nonlinear ODEs are extremely difficult or most of the time impossible to analytically solve. The other one is sometimes basically you only can simulate the environment. Modeling the environment and coming up with functions and differential equations is basically impossible. Like when you are simulating the self-driving cars, you cannot coming up with differential equations for all sorts of things that the self-driving car will be exposed to, right? Who is going to jump in front of it? How is it going to deal with the uncertainties in the environments on the roads and so on? So that's where you can only simulate them. Like, for instance, for self-driving cars, there are simulators like Carla and so on, okay? And if you want to do research on these here, you see, this Carla is your open source simulator for autonomous driving research. If you want to work on them, you can use this kind of thing, and that's basically the only thing you have. And reinforcement learning works very well with them. And sometimes not only you cannot model the environment, not only you cannot even solve those equations, sometimes the only way to collect information about environment is to do actual physical experience. There is no way that you can model, or there is no way you can easily simulate, like when you are trading stock market, okay? You really have to go and do that. Now, I know when people want to get into a stock market, there are these kind of simulators for them that they do not really invest actual money. It gives them some kind of virtual money, like if you go to Forex, correct? You see that in order for you to learn, it gives you basically some kind of virtual money, but the transaction that you do mimics the reality ones, okay? And that's the only way that you can do it. Now, by the way, it seems like I made a typo here. This is like this, FO. Yeah, you see, I'm not good at it. I never do the stock trading myself on that kind of scale. So yeah, still, although I know a little bit about it, but yeah, I still make mistakes. So finally, what are some real life applications of reinforcement learning? I said you use it all over the place, like where? So one place is robotics. When you want to deal with motion control, manipulation, and locomotion, you can do that, okay? Many times, as I said, with leg robots, with like the robots in Boston Dynamics and so on, when you want to do drone navigation, adaptive grasping, and so on, you can use reinforcement learning. In industrial automation, if you want to do process optimization or adaptive assembly, okay, you can do that, like for instance, hybrid force motion control or trajectory optimization. In autonomous vehicles, it used quite a bit a lot. Then in gaming and simulation, that's one of the biggest plays for it, okay? That's one of the absolute biggest plays for it, that you can see reinforcement learning is used in finance, is used a lot in healthcare, okay? Even for treatment recommendations and drug discovery, for personalized dosing and so on. It can be used in digital twins and smart manufacturing. This is the new kind of new area, right? Which it can be used in natural language processing, that your agents over time learn how to interact. The chatbots, they learn how to interact with the user to gain the maximum satisfaction and their highest rating of the chatbot. Over time, you see, reinforcement learning can be used, okay? Right? So when you're dealing with users and a chatbot is dealing with them, can you model that satisfaction with a mathematical function? Well, that's not very easy to do that. And most probably, even if you come up with something, they are so highly nonlinear, you cannot solve it. So the best way is to actually let those chatbots deal with actual people, get some actual satisfaction ratings, and try to maximize that. And that is the area where reinforcement learning is great. So hopefully this video was useful to you. You learned some introduction to reinforcement learning. And in my next 2 videos, we're going to talk about solution to this reinforcement learning problem. And finally, using neural networks for that deep reinforcement learning. Thank you so much. I'll see you in the next video.